Now let's take a look at what we saw in the chapter. So I go back to the analysis of cross-sectional data, and at the very end of this chapter, we'll see those plots right here. So this is showing us, the first plot is showing us time on x-axis and distance from the on-ramp. So 0 means that this is exactly on the on-ramp, and this is upstream of the on-ramp, and this is downstream. And so upstream, because of the traffic, now if you take a look here, uh, we see that vehicles are slowing down a bit, right? As they're moving along the ramp, they're slowing down a bit. And over time, you will see even more slowing down, and this will become a bottleneck. So that is causing the upstream congestion. So the red and orange lines or colors here represent uh, traffic breakdowns. The first one here is using the formula of flow of 1 divided by the average of time headways. That's the formula of the flow that is used on x-axis here, and on, sorry, y-axis here, and on x-axis we have density, which is estimated using Q over V right here, right? So the flow is defined like this. So that's the plot, right? So what do we see here? We have the fundamental diagram, the black line. We also have these data points for uh, at 1 kilometer from the on-ramp, 3 kilometer, the triangle, 5 kilometer, this orange square, and then 7 kilometer, the blue square. All of these represent the points. If we first look at the fundamental diagram, this is showing us that this is the free flow branch of the fundamental diagram. Remember, fundamental diagram represents identical driver vehicle units, and also assuming that the speed distribution is not changing over time. And so this is the free flow branch, and then this is the congested branch. But the actual data points, although are plotted on top of the fundamental diagram in the free traffic, in congested traffic, it's not even close to the congested fundamental diagram. Here we see these point clouds, and we see that the maximum density that they go to is less than 60 vehicles per kilometer. But these sets of plots also tell us that using different formula for estimating flow and density will give us different results. You can clearly see these different results. This last one here, this is directly from the detectors that are available in the simulation. This is the flow using the definition of flow, the number of vehicles at a particular location for a given unit of time. And the unit of time here is 60 seconds. The density rho is the number of vehicles in a kilometer, right? So this is directly available from the detectors in the simulation. And these are making very similar figure like the fundamental diagram. So we have the free traffic, and then we have the congested traffic, this line. Yes, there are some outliers here, but I wouldn't say these are outliers. There are other point clouds here, but we see the clear pattern, which is just like the pattern in the fundamental diagram, although the density is smaller than what the fundamental diagram suggests. But then in plot C, we have flow Q, again estimated as this formula, versus density using flow divided by harmonic mean speed. So this is C. This is what we get. A different interpretation here because the plot is different. In part D, we have flow, which is Q star. So this is the average of 1 divided by the time headways, and the density is Q star divided by harmonic mean speed. So that's D, right? Again, very similar pattern like the fundamental diagram. So this seems to be a good estimation because we're using harmonic mean speed, which we know is a better representation of space mean speed, and flow is also a better representation of the actual flow. And then we have the part E, which is using the flow as this definition, and density as Q star over VH. So every single of these plots give us a different result. So that's why it's important that we know exactly what definitions we are using for flow and density. So now if you look at this, you can clearly see that the traffic breakdown is moving upstream, right? This is now 1 hour 34 minutes of simulation time, and it takes 2 hours for the simulation as specified in the simulation settings. So this is the result that we get. This is unlike any of the plots that we saw in the chapter. And I have already emailed the authors as to why do we see these differences. I have made sure that the IDM model parameters that we have used are the same as mentioned in the book. It's in table 12.2, I think, in chapter 12. So we are using exactly the same things, but we are getting somewhat different results. These triangle data points represent just the most closest detector of 1 kilometer. So here we see a higher density between about 62 or like around 50 to 70 vehicles per kilometer.